Hi y'all, this is section 2.6, the Intermediate Value Theorem. Hopefully you've already taken a moment and read through example number 1 and given it some thought before you press play on the video, so you can see if you had some things right before you even started. Okay, so this is an example of two people are running a race, okay, and we want to, for part A, show that there is a time between 1 minute and 3 minutes after the race begins at which each one is running exactly the same speed. Okay. For part B, is it possible to tell what that speed is? Explain. And part C, is it possible to tell when that speed occurred? Explain. So, what I'd like you all to do on this problem, I know on this problem it might feel weird because the time is in terms of minutes, and their speed, was it speed? Yeah, and their speed or velocity was in miles per hour, okay? Now, fortunately, on this problem, we are not going to be doing any sort of definite integral, so we don't need to worry about multiplying those two units and having those units cancel. So it's okay that they don't match for this particular problem, okay? So what we want to do is we're talking about after 1 minute, and then after 3 minutes, they told us how fast these students were running. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so after 1 minute, I had that Alyssa was running 5 miles per hour. So there was Alyssa. And Ryan was running 8 miles per hour. So Ryan's in red there. After 3 minutes, Alyssa is now running 9 miles per hour, where Ryan has slowed to 3 miles per hour. So Ryan is over here at 3, and Alyssa is up here at 9. Okay. Now this is a key to this question. It says, assume that each runner's speed is a continuous function of time. Hopefully that makes sense because they're running this race, they want to win, and so they're not going to stop running. So they will have a speed value for every value in between 1 and 3 minutes. Okay. So this is really what the intermediate value theorem is getting at, is the idea of, for part A, we don't know exactly how Alyssa's dots are going to get connected. Maybe at 1 minute she was traveling 5 miles per hour, maybe she stayed traveling 5 miles per hour and then shot up really fast at the end. Or maybe she was, going up and down. She's running 5 miles per hour, 6, dropping down to 4, coming back up to 7, dropping back down, and then going back up to 9. We're unsure of how these two dots are going to get connected, but we do know for sure that they get connected, okay? So I'm just going to go ahead and say maybe she was just, kind of speeding up and up and up as she was moving in that direction. Okay. Ryan is the exact same thing. Ryan was traveling at 8 miles per hour after the first minute, but he slowed down to traveling 3 miles per hour after the third minute. Again, we do not know how these dots get connected, but we do know that they get connected in some way. So let's say Ryan was going crazy. He was going fast, and then all of a sudden he started getting slower and slower. So let's say he looked something along those lines. Okay. So for letter A, it said show that there's a time between those two at which each one is running exactly the same speed. So hopefully we can see here where these two lines cross, that right at this certain time, wherever that time was, looks like it's 2, but it just happens to be right in the middle, they were both running the exact same speed. Okay. So part B, is it possible to tell what that speed is? And then part C, is it possible to tell when that speed occurred? And really the correct answer to both of those is no. Okay, for both of them. So all we know is that these two dots get connected, but we don't know where they're going to cross and at what speed they would cross at. Okay, so all we know is that they will cross somewhere because both of the functions were continuous. Okay, so I don't know if that's making sense or not, but both of those would be a no. And this is what I'm trying to get at again, is just to imagine that if you have two dots plotted on a graph, so if you know that f of 2 equals 3, so f of 2 equals 3, and f of 5 equals 7, 3, 4, 5, 6, 7. So you have these two dots, okay? You have these two dots. You have these two dots. Okay. So for this example, I just wanted you to graph these points and then draw 3 different situations of what f could look like over the interval from 2 to 5. Okay? If all you know is that we have these 2 points, realize that you could have an infinite number of situations. Okay? I just wanted you to graph 3 different situations. It's obviously the most straightforward, or maybe the most easiest. I know that doesn't make sense, but most, the smallest distance between these 2 points would be this straight line. So obviously if it just got connected in some straight line, it might look something along those lines. Okay. I never said anywhere here that f had to be continuous, so maybe you have something along these lines. Okay. Or maybe you were thinking, oh, this looks like a nice, parabola or something along those lines. And realize your picture could have a million different possibilities. So you could have actually tried this on your own, and you would not have those pictures. Okay. But what I'm trying to get at here is that if we can guarantee that f is continuous, okay, and this will only work, the intermediate value theorem will only work if f is continuous. Okay? Maybe some of you drew continuous functions for all of your pictures. I didn't. The first example and the third example are continuous, but example number 2, this middle guy, is not a continuous function. Okay? So we should not look at him when we're looking through these situations. If you drew 3 different continuous graphs, you can use all 3 of them and see if you can answer these questions. Okay? So if we can guarantee that f is continuous, then for letter A, is there some x value in between 2 and 5 that you can guarantee gives an output of 6? So let's look at this example. In between 2 and 5. Okay, so we're looking on this interval. Is there some value in here that we can guarantee gave us 1, 2, 3, 4, 5, 6 as an output? Okay, so in this picture that I drew, there must be some c value when I plug it in that's going to give me 6. Okay. In this picture over here, this was 2 to 5, and I don't know exactly where 6 is, but 6 is somewhere in here. There would also be some c value that I could guarantee would give me 6. Okay, and that will be true for any continuous function if you were connecting those 2 dots, because we would call 6 an intermediate value in between our 2 outputs. And I'll write this very thoroughly in a moment when we write the definition. But we were down here at 3, and we were ending here at 7. So we know that 6 is an intermediate value in between 3 and 7. So we would have to guarantee that there would be that value as long as f is continuous. Okay. Same question here for part B. We want to know, is there a guarantee that we're going to get an output of 3.5? So if we find 3.5, 3.5 is clearly in between 3 and 7. So we could also guarantee that we would hit 3.5. Okay. Over here, continuous function 3.5, I knew for sure I was going to get that value. Okay, so yes, we could guarantee that we would have 3.5. For letter C, is there some x value from 2 to 5 that we can guarantee gives an output of 1? Okay, now be careful because 1 falls outside of your outputs. Okay, so if you were getting connected with a straight line, there is no guarantee. In this example, I connected those 2 dots, and 1 falls outside of 3 and 7. It's not an intermediate value. So we cannot guarantee that there would be a value of C that would give us an output of 1. Okay? Now realize that it doesn't mean that there is not an output of 1. I mean, check this guy out, right? Down here, let's say this is 1. Maybe there actually is multiple C values that give you 1. So we could call that like C sub 1 and C sub 2. But we could not guarantee it unless we actually knew what f looked like. Okay, so this would be a no. Again, the reason is that 1 does not fall in between our 2 outputs, and I'll write that very formally in the other problems. Okay, so what is the intermediate value theorem? Let's make sure we can state this. It's a pretty straightforward theorem in that it kind of makes sense. I don't know if that just made sense. But you'll rarely have to quote it on the AP test or on my test, okay? It's more about this whole, can you guarantee a certain value over a certain interval, okay? So first of all, let's break this, whoa, my bad. Let's break this number down. Intermediate, you want to think of that as like middle, right? You're not beginner, you're not advanced, you're in the middle, you're intermediate, okay? Value is like a number. What else did I call it? It's an output though, okay? So remember, we're talking about outputs, not inputs. Okay, we're looking at the outputs. And the theorem is like your rule. Okay, so here's the rule. If, and this is a big if, y'all, if f of x is continuous, f of x has to be continuous. So if f of x is continuous, okay, along the closed interval, so from a to b, including a and b. Continuity at an endpoint, by the way, just means that there has to be a dot sitting there. Okay, so as long as when you plug in a, you get a dot, and as long as when you plug in B, you get a dot. And you get a dot for every value in between a to b as well. That's what continuous over that interval would mean. Okay. Then, we could say there will be, okay, and they'll call this some c value, so some c, where a is less than c, which is less than b, so basically c falls in between a and b, okay, where f of a would need to be less than f of c, which would need to be less than f of b. Okay. And those are the words that go with intermediate value theorem, so you should definitely have that for your definition for your summary sheet. But you should also have a nice visual. Okay, and I hope there's enough room on your paper to draw this same picture. Okay. So we want to think of the intermediate value theorem if this is f of x, and these are your x values. Okay. And if you are starting, you plug in a and you know you get some output. And all we can call that is like f of a. Okay. And you're plugging in b, and you know you get some output. And all we can call that is f of b. As long as you know that this function is continuous. You don't know how these get connected, right? They can be connected in lots of different ways, but as long as these two dots get connected, okay, you know you will hit every value in between these two values. So you will hit every value in between. So these are your intermediate values, anything in between these values. Okay? And so if I picked, let's say, this as my special value, I could say, all right, here at this c value, I know I'm hitting this, some f of c. And I could hit every f of c in between here. I can guarantee that I would hit every value in here somewhere, at least once, in this interval. Okay, so there will be some c that when I plug in c will give me every output from f of a to f of b. Okay, so in your definition for intermediate value theorem, please have the words and then also have some sort of picture showing that the c value will fall in between a and b as long as the output falls in between f of a and f of b. Okay. So from here I'm going to show you two examples, one with no calculator and one with the calculator. And the tools that we'll use on our calculator we'll use a lot this year, so you want to make sure you know how to press all those buttons on your calculator. Okay. And this is often how IVT, Intermediate Value Theorem, questions are asked. Is there some c value? So notice you're going to be stating yes or no. Okay. In 3 to 5, that's the interval, that you can guarantee that f of c will equal 12 if f of x equals x squared minus 4. If yes, we're going to find the c value. If not, we're going to state why not. Okay. So if possible, the best thing to do on these types of problems is to give yourself a nice sketch so you can imagine what is happening over this interval. So hopefully we know that f of x would be a nice up parabola, and all we've done is go down 4 units. So 1, 2, 3, 4. So we have something along those lines. Okay. And we are talking about specifically over the interval from 3 to 5. Okay. So we need to get a good idea of where 3 and 5 is here. So I don't want to put my tick marks until I know kind of where my outputs are. So that's actually one of the earliest things you want to do is find where you're starting and where you're ending. So figure out what f of 3 is. That's, you know where you're starting. And then figure out what f of 5 is. So f of 3, you plug that in here. You have 3 squared minus 4. So 9 minus 4, we must be at 5. And then plugging in 5, we have 5 squared minus 4. 25 minus 4, we must be at 21. So obviously, when I plug in 3, I need to be up here at positive 5. So maybe let's do something along these lines. 1, 2, 3. So let's call that point right there 5. And if I plug in 5, 4, 5. Obviously I didn't draw my parabola big enough here. Oops, put the eraser back in the right spot. Alright, just pretend that's a parabola, y'all. And then if you plug in 5, you're up at 21. Okay, so you plugged in 3, you're at 5, and you plug in 5 and you're up at 21. Now I know my picture looks kind of linear because I just resketched it, but it's really part of this parabola. Okay, so here's the question. Is there some c value in between 3 and 5 that you can guarantee f of c will equal 12? Okay, so first step is to state whether or not f is continuous. Because if f is not continuous, you cannot apply the intermediate value theorem. Okay, so is f of x continuous? Yes, f of x is continuous because it's a polynomial function. Anytime you have just like a quadratic or a cubic, that is a continuous function. So we can say, let's not say therefore yet, we haven't made any statements. We can say f of x is continuous because f of x is a polynomial function. Okay. Once you've established that the function is continuous, then you know that the intermediate value theorem must apply. Okay. So from here, you could state, so is there going to be some c value? So now you need to look at which value they're asking you for 12. So now you're saying, does 12 lie in between 5 and 21? So yes, right? 12 is going to be somewhere in here. So I want to figure out what value I'm plugging in here. I need to figure out that value, that when I plug in that specific c, I'm going to get 12 into my function. Okay. So because f of x is continuous, because f of x is a polynomial function, and because 12, our desired output, falls in between our two other outputs. So when I plugged in 3, I got 5. So I can either write f of 3 or 5. And f of 5 was 21. So there's the intermediate part. 12 is an intermediate value in between 5 and 21. So because the function was continuous and 12 is in between 5 and 21, we could say yes, there is some c value. So because f of x is a polynomial function which is continuous, and because 12 is in between, we can say therefore, yes, there is some c value. There is some c where f of c would equal 12. Okay. Now they said, if yes, find c. So we want to know, when does f of something equal 12? You're literally going to take the equation and set it equal to 12. So when did f of x equal 12? So f of x was x squared minus 4. So x squared minus 4. And now we're going to solve this. So add 4 to both sides. X squared equals 16. To undo squared, use square root. Don't forget plus or minus. So we get x equals positive or negative 4. But remember, we were just caring about this interval from 3 to 5. So you're only going to pick the answer that lies in that interval, which happens to be positive 4. So we could say x equals 4, but realize x equals is the specific c value that we're looking for. So we could say, yep, c equals 4. Okay. So all of that is the answer, doing all of this work and then stating the actual answer. So this is an example without your calculator. Okay, so you should be comfortable setting the equation equal to the desired output and being able to solve. But you may get to a problem where you set that equal and you can't solve it, which will happen in the next problem. Okay. So let's try this fourth and last example. So is there some c value from 0 to 1 that you can guarantee g of c equals 1 if g of x equals this guy here? Okay, x cubed minus 3x squared minus 6x plus 8. If yes, we're going to find c. If not, state why not. Okay. So I've already graphed this for you from my graphing calculator. X cubed minus 3x squared minus 6x plus 8. I would not expect you to know exactly where that cubic function is. I would expect you, though, because there's a 1 in front of the x cubed, to know that it ends like this and it begins like this. So as long as you knew it had this general picture somewhere. Okay. I don't care if you knew where it was in orientation with axes. Okay. But then knowing that you're going from 0 to 1, I want you to know, where g of 0 was. If you plug in 0, obviously we're just at 8. And if you plug in 1, so 1 cubed minus 3 times 1 squared minus 6 times 1 plus 8. So if you do that correctly, it looks like we should be at 0. Okay. So we have g of 0 was 8. So obviously that dot right there was at 8. And then g of 1 was 0. So those are the two dots that we're working with. Okay. Again, how do we know that the intermediate value theorem is going to apply for this problem? We know that it will apply because g of x is a continuous function, because g of x is just a polynomial function. All polynomial functions are continuous. Okay? So we know that the intermediate value theorem will apply. So IVT, and you can use abbreviations. We'll have 3 theorems. Intermediate value theorem, extreme value theorem, and the mean value theorem. IVT is fine for intermediate value theorem. So I know that IVT will apply because g of x is continuous And last time I wrote it out kind of differently. You can write it here because g of x is continuous. You can say because polynomial. That's fine. So IVT will apply because g of x is continuous. Now, one thing I did not write out yet, realize we were starting here at 8 and ending here at 1. No, at 0. And our desired output was 1. So we wanted to know right here, what C value can I plug in and it give me 1? But hopefully we can see that 1 is clearly in between 1 and 8. Okay? And so we should have said that here because, now in this case, it's slightly backwards. F of 1, which was, no F in this problem, G. G of 1, which was 0, is less than G of 0, which was 8. And the desired output was 1. So hopefully we can see that 1 clearly falls in between 0 and 8. Okay, so that's how we know that the intermediate value theorem will apply. So what did I write so far? IV2 will apply because g of x is continuous, because it was polynomial, and because 1 falls in between the two desired outputs. Okay, so therefore, yes, there will be some C value. Yes, there will be some C where g of c equals 1. Okay, so to figure that out, let's write that, where g of c equals 1. So to figure this out, you're going to take what g of x equals and set it equal to 1. So g of x was this stuff. So when does g of x equal 1? That was x cubed minus 3x squared minus 6x plus 8. We want to know when that equals 1. Okay. So on the last problem we got to this step, we could actually solve this for x. If I tried to solve this for x, I could subtract 1 from both sides. Then I would have negative 6x minus, or plus 7 equals 0. This is not going to be anything that is factorable. Okay? So this is a calculator question. Okay? From here, we're not going to be able to solve by hand. So what I'd like you to do is get used to using your calculator to solve when a certain equation is set equal to a constant. Okay? If this is typed into y1, this whole left side, okay, the original equation, and you type this, whatever you want it set equal to, in y2, okay, then you can just look at the points of intersection and find out exactly where they're crossing. Okay? So let's look at the graphing calculator. I already have my y1 typed in. For my y2, I'm going to type in that constant of 1. You're going to work for me? No. Oh, we're in this mode. Hold on. Okay, so y2 is going to equal 1. So if I graph the original equation and 1, graph, you'll just see this nice constant flowing through here. Okay? I want to find out exactly where they were crossing, right there. I want to figure out what value can I plug in that will give me 1. So I want to find a point of intersection. So I'm going to go second trace, which is calc, second trace, which is calc, and we are calculating that point of intersection, so 5. Okay. So the first curve, it doesn't matter which curve you're on. First curve, if I toggle down, I press down, now I'll be on the second curve, and you can see right there. And then up, so it's just going between y1 and y2. So first curve, I want to find this point of intersection, so clicking right there is totally fine. So I'm just going to say enter. Then it will move to the second curve automatically, and I'm going to go ahead and say enter. Okay. And then it's going to say guess. So yes, guess, so enter again. Okay. It moved, now it's blinking on that point of intersection. So this right here is your answer. Okay. So I'm actually going to pull that over so I can see exactly what it said at the bottom. So this value right here, remember you need to be accurate to 3 decimal places. Okay. When y was 1, this was your x-coordinate. Okay. Now realize again, technically there was that point, and that point. We technically had 3 points of intersection. But we're only worried about this one because we're worried only from 0 to 1. Okay. So I would say x equals, or c equals, this value here, 0.8887. So technically I'd accept 2 answers, 0.888 or 0.88. You could look at this guy and round 8 to 9. So those would be the 2 acceptable C values. Okay. All right, I hope this made sense. Intermediate value theorem is always kind of a weird theorem. It feels very intuitive, but please summarize and write out a few questions, and look forward to discussing this with you in class tomorrow.